So hey everybody, we're gonna start in just a few minutes. Just sending out a social blast really quick to let everybody know that we're going live. Welcome to the Audio Programmer Meetup. So we got quite a few people that are tuning in. Here we are. We got over 50 people tuned in, and we're just going to give a couple more minutes just for everybody to join us and get logged in, get comfortable, grab your popcorn. It's going to be a really fun meetup.
Yeah.
Okay. So,
All right, should we start?
yeah, let's go ahead and get started. Take it away,
All right.
Timur.
All right. So, hi everyone. Welcome to the Audio Programmer Meetup. My name is Timur. I'm super excited to be here tonight. This is actually the second time we do the Audio Programmer Meetup. Last time we had it in the Strong Room in London just 5 weeks ago. That was a really cool event, and we also had a live stream. Obviously this time we have the live stream only for obvious reasons. As you can see, I'm actually at home in my flat right now where I've been for the last 5 weeks. So actually the last Audio London meetup was the last time I actually went out and talked to real people. So yeah, it's a bit of a challenging time right now for many of us, but I think it's also a great opportunity for us to, first of all, come together as a community of audio developers, and then also, kind of try to figure out how to organize ourselves better and more efficiently online, and how to do these meetups and how to include more people. And also, it's an opportunity for us to have more awesome speakers who are maybe not in London, not local, and get them here. And we actually have 3 of them here live with us tonight, and they're going to answer your questions. And also, obviously, we have Josh, who is also online. Hey, Josh, you want to say a few words as well?
Yes, hi. Once again, as Timur said, just thank you all for coming here. And we're so happy that these presenters have been so gracious to submit some content for us as well. And one thing that we've been trying to do is, in the past, some of the audio developer meetups have been very centered around maybe one type of audio development, and we're trying to spread our wings a little bit and get some diversity in our talks in terms of content and also in terms of people that are coming to speak. And so we have a really exciting program for you this evening. We have Bogdan, Vera, who is a lead engineer at Dreams for the Sony PlayStation game, and he's going to be talking about game audio. And this has been a subject that a lot of people in the community have asked me about, is more talks that are around game audio. So anybody that's tuning in for game audio centric talk, this is a great talk to check out. We also have Christian Steinmetz, and he's going to be talking about a real-time machine learning plugin that he has been working on. And we also have Brett Porter, who's not quite here with us yet, but he's going to be giving a talk on MIDI 2.0, which is another subject that so many people are curious about, to see the upcoming changes to the standard, and just looking at how revolutionary this is going to be for people that are looking to develop forward-thinking applications for music, and also our end users who are going to be using these applications. One thing that I'd like to say, I'm just going to share my screen for a moment for you, is I would like to give big thanks to our sponsors. So we have our sponsors, Focusrite and Sonex, who have been very supportive in these audio developer meetups, and we're so happy to have their continued support even as we've had to go online to these to the virtual method of giving these. And I also wanted to tell people about our next virtual meetup, which is going to be happening on the next second Tuesday of the month, which is the 11th of May, 6:30 to 9. And we're ready to announce one of the talks already, who's going to be Stefano Zambone, who's the CTO at Elk, and he's going to talk to us a little bit about his company. And of course, there are going to be more talks that are going to be announced. So thank you to Stefano for joining us next month. Another thing that I wanted to touch on very quickly is for other people that are looking to perhaps present a talk or give a demo. I encourage you to submit a talk. You don't have to be a professional audio developer. We also encourage people that are coming up and just getting into development to also submit as well. We want to, as I said before, give a wide range of talks that are across the spectrum of audio development. And you can submit your link here at the audioprogrammer.com/submit a talk. And the other thing I wanted to say very quickly is if you've been on the Juice forums at all, then you would have heard about the announcement of Juice 6, which is coming out in June. They've formally announced today, and they're going to be slowly rolling out different features. And there's quite a bit that they've offered in this new installment of Juice, and I would encourage you to go check out the formal announcement over at forum.juice.com. And that's everything from me.
All right. So I think, we can actually start with the first talk. So we now tonight have Bogdan with us. Bogdan works at a company called Media Molecule. He's designing and developing music and audio tools for Dreams, which is a user-generated content game for the PlayStation 4. And I actually realized that I have a PlayStation 4 right here next to me, so maybe I should really check out this game. So I'm definitely going to do that. Really interested in this. Bogdan's going to be talking about the development history of this game and kind of the challenges faced while developing it. I'm really excited to hear more about that, and maybe afterwards actually try the game.
Great. So I'm just going to share my screen now to give these talks. Another thing that we've done is we've actually asked the presenters to pre-record their talks, and I think it puts less pressure on the people that are giving the talks, and also prevents us from having any sort of technical hitches in sound. So here is Bogdan.
Hello, my name is Bogdan Vera, and I'm here to talk about the development of player-driven audio tools for Dreams. And I come from a company called Media Molecule, which makes video games. So what is Dreams? Dreams is a UGC game. That stands for User-Generated Content, and it's on the PlayStation 4. And it's in some ways a spiritual successor to a previous game we made called Little Big Planet, which also let you do similar things to Dreams. And that is make content with the same tools that we use to make the game. So the tools that we design for ourselves, the players also get. And you can make everything from games to animations to art, music, sound art, and even stuff we haven't maybe thought of yet, because you can put all these things together in the same place and make anything you want. It's got a built-in social platform called the Dreamiverse, where you can upload your creations and instantly share and collaborate. For example, if you make a piece of music, I can put it in my level. Or if I make an audio recording, you can put it in your piece of music. Or I can sculpt a tree or a rock, and you can put it in your scene. So in Dreams, you can do a lot with audio. You can create and remix and share songs and sounds. You can implement game audio, so dynamic music, and audio that's linked to game events. And you can produce reusable assets for other users and publish them to the Dreamiverse and collaborate on them. You can create interactive experiences that aren't just games, but you can make installation-style art or playable instruments that exist within the play mode of the game rather than the edit mode, so people can just play them. And you can link to the real world, of course, with the controller, because you can just do some mappings to the controller buttons. And you can record audio and share sound libraries with other users. And one cool thing is you can perform live music. You can just take your PlayStation on stage and use it as your main audio workstation for both audio performance, or music performance, and live visuals if you want to, because of course it's a game, so it does that. Some of the underlying principles that we followed, even from the early development of Dreams. The main one that always came up is flow. And flow is this idea that a creator or a performer can be in this state of mind where they're thinking about the big picture of what they're doing. For example, a guitarist who knows a song really well and is just playing. They don't have to think about the chords or like the shape of the guitar, or maybe even the audience around them, or the microphone they're using. They don't care about those details. What matters is the moment-to-moment aspect of performing. And that's what we wanted to emphasize in these tools, as opposed to an editor mentality, where you go into different menus and stuff to do various things. We also wanted to emphasize performance, so the idea that, again, instead of going and editing things, you do stuff with your hands in some way, directly, like a performer would. And that doesn't apply just to music, but it applies to graphics and stuff as well. And even animation and stuff like that. I mean, our characters are kind of performed via a form of puppetry. The other big principle that we followed was integration and generalization. So the idea that your animation tool can be the same thing as your audio tool, can be the same thing as your logic tool. And we did do that, and I'm going to talk about that in a bit. And very importantly for Dreams, we didn't want to just go make another audio workstation, because there'd be no point, there's other ones already. We wanted to make something that feels cool and fun to use with a controller on a console or from your sofa, but that we can also use to make our game to a level of quality that we'd be satisfied with. So basically the challenge there is to create a fun game that you can play on your couch that lets you also make entire original games and also great music and audio, which sounds basically impossible. And yeah, it was a good challenge, and I think we gave it our best shot. So some examples here of other things in the game that follow these principles are things like the fact that we don't use polygons for our models. In other games, characters and levels and stuff are made out of polygons. Our models and characters and stuff are made out of just sculpted signed distance fields. Basically, the users just use the controller and they move around in 3D and they sculpt these shapes. They don't have to think about the vertices and the normals and all those things. And we don't use textures because, again, like mapping bitmaps onto polygons is a very technical thing. So in Dreams, you kind of just go and actually sculpt in the details yourself with the controller. But you can also use these tools that we've developed to quickly achieve a certain aesthetic that fits with the game quite well. So with a couple of movements of your controller, you can loosen up these sculpts to get these impressionistic painterly effects, which give it a certain visual identity. And the UI itself had to be simple, but also powerful. And we wanted to avoid what we call overflow menus, which are these menus where you normally, like when someone asks you for a new feature, like the polygon normal inversion / slicing tool, you go and put that into the menu somewhere in this overflow submenu where you shovel your features. And we wanted to avoid that because we didn't want to have all these menus everywhere. So in many cases, when someone asked for a feature like that, we either said no, or we found a way to combine multiple other tools to be able to achieve that effect. So maybe in the case of the thing I just mentioned, you would do a certain gesture with your controller in a certain state. But it was difficult to apply similar ideas to music and sound design. And the problem is that most people, even children, would understand how to draw a stick person or a tree or a house. You know, they have this innate understanding of what a house or a person is shaped like. But people don't have an innate understanding of what music is shaped like. Because music is this abstract internal representation of something quite logical. Which means it's hard. There's no way you're gonna take someone through the whole process of understanding musical theory to make a song. So we had this issue where, it was just a bit too abstract, and we had to figure out a way to bridge that gap. But there's also this issue where people feel this reverse elitism, where they feel like this is just not for them, not even gonna try. It is for someone else who knows how to make this kind of music. Maybe they'll feel like it's something they'll be judged for if they make something and it's bad. Whereas people who normally play video games, video games have challenge, but you're not gonna be publicly embarrassed over a video game. So when I came onto the project, we had some audio in the game, but it was all in these kind of debug technical menus. And the thing that was missing was the tool set, the interactive aspect of it. And a lot of ideas were being floated around. People kept saying stuff like, it's gotta be playful, and maybe you jump on mushrooms, and the mushrooms make notes when you jump on them. Maybe you can play the level, like say if I open a door, instead of squeaking, it makes a melody or something, and I can move the door back and forth and it would do that. Or that it would sound dreamy, this dreamy aesthetic. What that means, nobody could really explain. But to the audio team, it kind of maybe implied some sort of granular, scrambled, reversinated sort of thing. So there was an ethos there, but it was quite vague. Basically, for me, it was a matter of figuring something out to do. And on the PlayStation, you have to remember there's normally no keyboard and mouse input, so this whole thing must be driven with the controller. So you've got either the DualShock controller, which is a motion-driven thing, where you can point in kind of 2D space like a laser pointer, or you've got these move controllers that you can move around in 3D space. So basically, if you can sculpt trees with a controller, why not sculpt music, is what I was thinking at the time. So those early prototypes were inspired by what we could do with the sculpting and art tools. And for me, motion and shape was very associated with the rackets and stuff like that, like the idea of graphical scores that encode music in a more visual way. And I thought that was cool because everyone can kind of understand movement, shape, and color. But they maybe don't understand musical theory, so maybe we can make it so that music has and shapes and colors. So people just take it as programs. It's not how people music. And purpose it for everyone who can do the projects and
Okay. Can you hear me? I'm just going to try to rewind that back a little bit and see what's happening.
Course that encode music in a more visual way. And I thought that was cool because everyone can kind of understand the movement, shape, and color, but they maybe don't understand musical theory. So hey, maybe we can make it so that the music is expressed in shapes and colors, so people just think in those terms somehow to make music. Remember, this is for like everyone to be able to make music, not just for sound designers and composers. So basically, it's kind of rephrasing complicated music theory as this other hierarchy of parameters. And because we have motion control, of course, motion-based music of some kind would have been a cool idea, is what we were thinking at the time. So a lot of these early ideas were stuff like, hey, maybe you just draw these curves, left to right, and maybe you map pitch on the y-axis and x-axis is time. And you have this kind of classic graphical score thing, where maybe these curves get thicker and thinner to represent volume. Maybe their color is different instruments and stuff like that. So, quite simple stuff that you might see at NIME or something. And then it evolved into this thing where like maybe you just draw these shapes in a 2D space, and maybe time isn't an aspect of it, because we found quite quickly that people struggled with the time aspect of music. And by that I mean beginners or people who don't normally make music struggle to keep in time and play beats. So maybe you just draw these shapes and the game somehow does timing for you, so you just care about textures and stuff, so you make soundscapes and kind of avant-garde music. But the problem with this was that it was really academic, and the thing is, even though you can make these soundscapes quite easily, and everyone can, it's not everybody wants to make abstract avant-garde soundscapes. People want to make dance music and stuff. And the other issue was that the content team that we had said, no, I'm not using colorful blobs to make our AAA game soundtrack. There's just no way, basically. So this abstract, like post-tonal music thing was around for a while and then went away. But some of this stuff remains today, and you'll see that in a second. This 2D colorful blobs thing, it's still there as a core aspect. So basically at this point, there was this serious dissonance between needing to make a fun audio tool for gamers and also making it powerful and efficient enough to actually make a AAA quality an audio experience on there for our actual content. And of course, we have to use the same tools as our players, and we can't just ship a DAW either. We can't just ship Fmod or Wise. It's not something we can do. And why is that? Well, that's because we're a small dev team. Like, at most, we have 2 audio programmers between me and Alex Evans, our tech director. And we don't have the audio memory availability that you might have on a PC where you load gigabytes of samples. We just have, like, whatever's left after the game has allocated its resources. And then you have to tutorialize it, and it's not fun to sit on your couch and use a DAW. You want to do that at your desk. And a lot of other reasons. So at this time, there was this kind of terror, deep thought thing where I just didn't quite know what we can do about that. Maybe it was impossible. But a game audio tool needs a couple of things, and you kind of need these things to really get away with it. And you need obviously sound playback, some way of managing assets. So what are your samples and stuff? You need sequencing, so time, linear sequencing, and also dynamic sequencing. Implementation code of some kind, so maybe linking game events to things that happen in the audio engine. Spatialization, localization is a big one that we didn't think about enough at the beginning, which is different languages and translating voiceovers. And mixing, these are things that you need, and we actually did need all of these things in the end, and we had to make all of these available to our users. So yeah, were gamers going to be doing all of this on their PlayStation? That remains to be seen for a long time. The thing that really solved all these problems for us was this concept that we eventually came up with called an effect field, and this other thing called a soundstroke. And a soundstroke basically is one of these 2D space trajectories. It's the same thing as before, where you draw with your controller from point A to point B. But we added this other thing called an effect field, and what that is an object that lives in this 2D space and has a central position, an inner range and an outer range. And it's effectively a form of preset interpolator, where your stroke is a synthesizer with a million different parameters. And as it goes into this effect field, the effect field asserts a change on those parameters. And they can blend with each other as well. So basically, you can now perform through this 2D space, not just with pitch and velocity and position, but with all of the parameters in the synth at one time. You can do these massive transformations. For example, I can have an effect field that applies 10% to volume, 50% to time stretch, minus 30% to grain length, and so on. And now I can go in and out of that field in time with the music, or according to some expressive curve I want to get. Or I can go, between 2 effect fields to get a wobble or something like that. So in a way, it makes fairly advanced concepts like automating a dubstep wobble or freezing a sound granularly a thing that you can express just with these colorful shapes. So a user might think, hey, how do I get that creepy ghost voice effect? Well, I stamp down the creepy voice effect field, and now I've got not just a static effect that's applied to my voice, but I can perform in and out and get these different transformations. And here on the right, you see this freeform view where these strokes live and the effect fields that they go through in this case. And the cool thing is these strokes also exist in time versus pitch domain. And on the left, you can see that, and that's just the piano roll. And each one of these corresponds to one of the notes in the other view. And they can transform from one to the other with a lerp, effectively, like an animation that shows you where all of these notes go in the other view. And you can do stuff like select in one view and edit in the other view. So basically, these sound strokes are stored musical data that exists in this 2D space, while also containing some temporal data. And every single one of these strokes is related to a single voice, which is a full synth instance. So there are other preset interpolation schemes out there that are really cool, where normally you have a synthesizer, VST or something, and you interpolate between the different presets using a little positional knob thing. And as you go between them, it lerps the synthesizer together. In our case, each one of those strokes is an individual synthesizer. So in the same instrument, I can perform in different parts of that space and have totally different sounding strokes, and have all this blending going on. So it's kind of cool because you can kit bash with these effect fields. You can make your own and publish them for other users, and it just makes you think differently. It makes you not worry about animating automation curves, but more about how can I perform, like I said before, with my hands to get these expressive curves. Because like on a keyboard, for example, if I want to apply an effect, I have to basically play with two hands on the actual notes and maybe move a dial or a slider or something with my other hand, which means I need to take my hand off the keyboard. In Dreams, you can basically perform all these notes with the controller buttons, but because you've got the motion at the same time, you can do these massive expressive transformations at the same time. So it's another aspect of the performance you can do. And you kind of, with practice, develop techniques naturally, almost as if you're practicing them on an instrument. You can basically get sort of like extended techniques for the controller instrument in a sense. And it lets you do really fun things like, for example, applying programmatic 2D offset to these performed strokes. Once you've recorded them, maybe you take a wire from a character moving in the scene and you map their velocity to X offset. So now your strokes are moving in and out of certain effects. So you can do dynamic music or sound design in that sense. You can apply LFOs on field strength. So you can have an LFO that kind of pulsates the effect field in place. So now when I play in that effect field, it's doing something rhythmic. It's basically applying the interpolation with a varying power. Or you can put these effect fields in the world. They can live with a spherical zone. So now when the character goes into these effect fields, it can be affected in some way. Its sounds, its footsteps, or its voice can have a certain effect. And it was very important for us that these effect fields can become as general as possible so that there aren't many other ways to do this. We wanted to have them as a primitive aspect of the system, which is why we gave them so many different aspects. They live in 3D, they live in timelines, as you will see, they live inside freeform view. You can drive them with wires and logic, you can do all these different things. And in terms of how you perform, how you actually get input into the game, you use the DualShock controller or the Move controllers. And basically you just use the front 8 buttons to play notes, and they're locked to a scale. So you've got one thumb for each, kind of like a kalimba, I guess. And you can tilt left and right to get octave shifts. You can use the touchpad to do semitone shifts and bends. And R2 is analog volume. So you've got 2 thumbs on the main buttons, and your index fingers are controlling the 2 triggers, so R2 and L2. And they do expressive analog things. But of course, you've got now this extra 2D pointing thing, where while you're performing notes, you can also perform all of these transformations. So this kind of turns the DualShock controller into an instrument, where you can become a virtuoso on it in some sense. And it can take a while to master. It's not easy to be really, really good at this immediately. You have to understand how to play it and then practice scales and stuff like you would on a normal instrument. And you can do really interesting extended techniques and quite advanced concepts. Like if I was going to explain granular synthesis to a 10-year-old who's never done music or sound design before, I would have to explain to them all of these, what are grains, how do they overlap, what's a grain interval, how many grains are playing at one time, how do you get it to be in time with the tempo. In Dreams, you just get them to stamp down these effect fields, and once they've understood those effect fields, they can also go tweak them in their options, in their settings menus. But they can get they can do things that advanced composers do with VST plugins just by kit bashing these effect fields together. And they might not know that what they're doing with this granular synthesis engine is actually quite an advanced thing that you'll learn in your master's degree or something. And basically sound effects in VO as well are all internally playing these sound strokes, which again are another primitive aspect of the system. And these sound strokes can be also put through the same process of a positional parameter blending thing. So even when you're hearing just someone's voice, it's actually one of these sound strokes that's bunched at one position. But you can do stuff like use the controller to blend together different sound effects and record expressive sort of gestures through sound effects and transformations. You basically do sound design almost as if you were in a sort of virtual Foley box. Here on the right, you can see the tweak menu for a sound, and this is the granular page. And this shows an interesting thing that we also implemented that I think would be awesome to have in other tools, which is that each one of these sliders isn't just a single value. they all have ranges, and what these ranges are basically randomization ranges. So for example, for the top parameter, whenever the sound will be triggered, it'll pick a value for that parameter between those 2 points. And you easily set that by holding down the button on the controller. So when you drag a slider, you hold down or equivalent of shift and then drag the slider, and you can make these ranges. But some of these sliders you can see have like these crosshatch diagonal patterns on them, and that's what we call spiciness. And spiciness is another range you can set on the slider, on the same slider, by holding down a different shift button, which is L2, the left trigger. And it's a range where from then on, whenever I hold down L2 during performance, all of these parameters will blend to. So I can easily make these sounds that have widespread randomization on all of their sliders. So whenever I press a note, it'll be totally different and varied. But then if I start pressing down L2, I can blend the entire sound to a different parameter set. And I can do that as I'm performing and also record that transformation. So in a sense, it's almost like an effect field applied to your sound, to your L2 button. So I think this randomization thing, I don't know why we don't do this in other systems. I guess it's because most synthesizers as plugins generally pull their parameters for each voice from the same set of parameters, whereas we have independent parameter sets for each voice that is playing, so they can be randomized on a voice-by-voice basis. So as I was saying, these two-dimensional positional strokes can also be viewed in a time versus pitch piano roll, and it does this lerp between them. And it lets you do this cool sort of workflow that takes a while to get used to, but is actually very powerful, where you can basically stay in freeform view for this more flow-driven mindset and go to the piano roll for this more editor-driven mindset. But because it's easier to switch between them with the button combo, you can do stuff like record a note in freeform view and then go to piano roll mode and just clone that multiple times to write your composition. Or vice versa, you can make something in the piano roll view and then take some of those notes, a sparse set, and then put them in other effect fields in the freeform view. So mastering these two views is a big part of how you make sound and music in Dreams. And what this does basically is it lets you playfully do automation just with the controller. So in essence, it's a system heavily colored by the tech that's available, which is kind of opposite to what we normally do, where we come up with aesthetics and then tailor tech to the aesthetics. In this case, we had the controller, we had some limitations. We didn't treat them like limitations and just made do with what's there. We really we kind of juiced everything that's available to get all of these features and tools that wouldn't work on with other control inputs. And ultimately, this means that these music and audio synth techniques can be explained to some users. We have a couple of tutorials. They explain how to draw these curves and stuff, and people do them. It's quite easy to make both avant-garde stuff and also kit bash together some sound effects and instruments to make a dance track or whatever. So now we have this system for performing music and doing sound design on a low level in this kind of flow performance-driven way. But what was missing was the audio workstation aspect of it. And in an earlier version of the game, we had this mode you would go to, the audio mode. And in that mode, you would do audio music, and you couldn't relate at all to the other tools. But what happened in the end is the animators were developing or designing a timeline for the animations, and the logic team were designing a timeline for the logic that they would do, like lights turning on and stuff like that, or character, AI or something. And we were designing a timeline for the music, and the obvious thing to really do was to just have one timeline that does all of these things. And that's what we did, and it's just called the timeline gadget. So basically in this final rewrite of Dreams, we integrated the audio engine with the logic timeline to kind of very organically function as a DAW with all the underlying playful features that I showed before, grinding away underneath within the inner elements, the sound that you put onto those timelines. And it was not easy to do. It's I know how to make a sequencer for MIDI or audio. I think everyone does. But it's tricky to communicate with the other teams within the development team to let you integrate all these specialized subsystems with the rest of their tools. Because obviously animations, for example, run at game rate, whereas audio runs at audio rate. An audio team needs certain features that maybe would kind of be annoying to animators if they were just there all the time. So there were always these caveats of like, hey, we can't have some of these things because they would influence negatively the rest of the team. But the best thing that came out of this was finding features that work for all of these teams and really hanging on to those ones. So in the end, the system only became fun when this tool unity was achieved. There's no separate editor for animation or audio. There's just one place. You make music in the world next to your logic, next to your trees and other things that are in the level or whatever, characters. You never have to change scopes or creative domains in any way. And basically, this all works with the controller motion input, like we needed it to. And it's got this consistent input metaphor. Again, the way you sculpt things is by flicking your controller around. The way you make music is by flicking your controller around, and same for animation. And that helps achieve this playful, performance-driven approach. And as I said, audio, music, and stuff all exist in the same system in real time. No compile times, it just, you hit play and you're in the level that you're playing. And you can edit it while it's playing. There's no export step of any kind. And all this fast prototyping generally leads right into development, so everyone's kind of liberated to create. Like I can make a prototype or a test project that ends up being the thing that we actually ship in the end. There's no, in-between version. Here's an example of like what a timeline looks like with different things in it. You can see like just some music clips, like kind of MIDI style. Remember, those are the individual sound gadgets, which inside have the squiggly stroke paths and stuff. But there's also some animations, and like there's a nested microchip in here, which is like a sort of sub-patcher that contains some logic. So you can put, for example, a microchip full of logic at a certain point in this timeline, and it'll trigger then and do whatever logic is inside. So it's kind of cool because you can take this timeline, which is effectively our DAW, and you can nest it within itself, so you can have nested clips within clips within clips. And you can also have microchips, which contain further clips, and you can infinitely nest them. I don't know of any other audio workstations that let you do this sort of clip nesting, but it's actually quite powerful and lets you do some fairly complicated setups. And we have to propagate playheads down this kind of tree of nested things. As for the Dreams audio engine itself, its main features are basically every voice is fully granular, always. And that's kind of our second big miracle. This is what we decided early on would define the sound of Dreams. It's that at any point, sounds in the level are ready to be stretched or scrambled or like frozen in some way. And even if you hear someone talking in the game or you hear a sound effect playing, it's always granulating, even if you can't actually tell, because the grains are normally overlapping perfectly. That means that basically it's always so easy to do these dreamy effects that we use them loads. It just colored the way the sound is in the end, in the game. So our main content, our main kind of story campaign is full of these granulated soundscapes, mixed in with kind of jazz and other stuff like that. But of course, because it's fully granular and it's always granulating, it's quite expensive. It's cheap to like stream in some audio and then just play it back on an audio channel, but we're always doing this granular stuff. And it's written in pure scalar C, which sounds like it would make it worse, but it turns out that you can write stuff in C without manually using SIMD intrinsics and stuff. And a good compiler, for example, Clang, will mega optimize scalar C to the point that we tested it against writing SIMD instructions, and it was as fast, if not faster. And it's just simpler, and it's easier to understand. So if you organize code the right way, you can get away with just compiler optimization. And basically, in terms of the capabilities of the sound engine and what you can do with it, we tried to get as much juice as possible out of the granular synthesizer. So we use that a lot to get our sound, as opposed to big sound libraries. It's rare in Dreams to have a piece of music that uses gigabytes of sound samples, because we can't afford it. So we have to rely on getting cool sounds out of the synthesis we have. And the cool thing about granular is it's comparatively cheap with other timescale manipulation methods like phase vocoders and additive resynthesis and stuff like that. And the other interesting thing is music, of course, is always live in Dreams. It's never bounced down to a track, which means that if I play your level and it contains some music, that music is playing live from the symbolic data that was stored, that was created by the original user. And you upload these creations to the cloud, and they're stored on our servers. And the audio samples that you potentially import or record are compressed in the level data, but we decode them on level starting to just raw PCM. In most games, you can get away with streaming chunks of audio as it comes in, as it's needed for the music, for example. But in our case, because we're granulating and the playhead of the audio voice can jump to any point of the sample, we need to have the sample in memory pretty much at all time. We can't on-demand decode stuff. We probably could, but it would be quite tricky, I think. But the cool thing is songs that are made from our own instruments that come with the game are all on the disk. The actual sample data is on the disk. So if I play a level that you made, I never have to download hundreds of megabytes of audio samples. But I can still hear any music you made because the samples, I already have them. Which basically means combined with the way we store our sculpts, our level data in this sign distance field representation, it means that basically our levels load extremely quickly, even if they have complicated music. And the way the audio engine is organized basically is there are these things called sound gadgets, which are the game level representation of a sound. And they update at 30 hertz from the game, and that includes the playhead updates from a timeline, for example. And we basically send to the audio thread at the end of a game update an entire copy, or rather a handle to the game that contains the sound gadget. And then on the audio thread, basically these sound gadgets spawn individual audio tracks, which are kind of a sounds instance on the audio thread, and those update at buffer rate, effectively. They update their playheads, and they do 3D panning. And then each audio track can spawn multiple voices. And each voice is like this stack of effects. They're always there. And these are the things that correlate or relate to the strokes that are wiggling around in the freeform view and reading out effect fields and stuff like that. And then each voice spawns out individual grains. And interestingly, our signal flow is quite unusual for an audio workstation, because normally in a workstation you have a mixer and inserts and stuff. But we have a fixed pipeline where voices always go through these effects, which you can toggle on and off. We have sends to 4 reverbs, which are IR reverbs, and 4 delays, which are just there in the sky somewhere. And then we send that. We also send out to panning and ambisonics for each voice. I guess that's done at the track level in the end. But yeah, interestingly, we don't have a mixer UI anywhere in the game. And I wrote here that mixer bad, but it's not that mixer is bad, but I think when you got the opportunity to make a new UI, a totally new interface, why go for something that's so old-fashioned when something that's kind of free form and kind of patching based is as powerful, but maybe easier to understand for some people, because not everyone has necessarily grown up with mixers. Someone who doesn't have an opinion on whether you need mixers or not might not care that there's no mixer in this game if they understand how to use this particular way of routing signals. So I have here some notes on logic programming as well, which is just talking about how Dreams handles effectively like programming. How do you actually make these games, and how do you interact with the music? And the idea basically is that programming in Dreams is done with these things called gadgets, which are these kind of data flow style boxes connected with wires, very similar to like pure data or something like that. But the cool thing is every parameter of every single one of these gadgets is exposed to wires and animation. So for example, timelines and music and sounds are all gadgets. So I can take a wire from any game parameter into any parameter of the sound in real time. Like maybe I can plug a character's walk cycle position to granular stretch or something. Or plug into one of these effect fields and do like a big multi-parameter transformation. But the game update basically is we just topologically sort these gadgets based on their wires. And animations that also drive these parameters also use these invisible wires. So we can sort the whole scene so that with them we can run in order over all these things. And all we do is we take an old game that has all the state from the old from the old frame, and we just turn every single thing into a thing from a new game. And at the end of this, we have a game, and then the audio thread takes a handle to that old game, and all the state it needs is there. Like if the audio thread wanted to iterate over, I don't know, over all wires or something, it can thread safely do so. Because we never touched the old game at that point. And so does the render thread. And then, the game thread will never read data from the other threads. There are a few exceptions, but we can't actually read the audio thread data because of determinism needs we have on the game update thread. And everything, which includes gadgets, which are things, has a unique power input that turns things on and off. So, for example, on a light, the power will be its light brightness. On a character, it might be visibility or something. On a sound, it's volume. But with the same input for volume, we detect edges, and when you turn power on, we just trigger the sound, so we detect these power edges. And the cool thing about using this generalized concept of power, which again is this kind of primitive thing in Dreams, is that we can use power, we can take aspects of how sounds work and put them onto other gadgets. So for example, lights have fade in and fade out, just like sounds do. Because we needed fade handles, like in any audio workstation, on the sounds. But because we did it with power, it doesn't have to be a special sound thing. It can just be a power fade on pretty much anything. Animations, keyframes. And I have some notes here on anti-creep, because as you can imagine, through all the development of this project, you get all these teams that are asking for features continuously. Remember, they're not using their normal tools. Imagine a team that makes a game that is used to using other tools that they would normally use, that are now making this game entirely with their controller on their PlayStation. They're not using Windows, they're not using an audio workstation, they're not using a 3D modeling program, they're just making everything in the game. They want everything they're used to. So basically we had to learn to aggressively say no, and I think that was actually very important. And you might say, well, say no to all these things means you end up not having all these cool features. But actually, if you say no enough, you can postpone things until you can figure out ways to combine those requests. So once you've got 10 requests that from the team, you can then match them up and say maybe these three features are the same one with the same tool. And again, as I said before, like avoiding these overflow menus, not shoving features into drop-down boxes. So now we got to talk about the bad, like what were the weakest points of our approach. And really the weakest points of this tool set are whenever we interfaced with external tools. Like whenever we were like, oh, we know how to do localization or audio pre-processing, we'll just use those tools instead of making our own tools. That's where everything was slowed down and annoying. And generally using our tools to make a level and make some audio for it is like fun and you're in the flow. But then when you have to go reach out into some other batch processor in Windows, that's basically, it shows why it's so much better to work with an integrated system. And if we designed those tools the same way as everything else we designed, it would have been much better for us, I think. But we fell into that, oh, we've done it before, we know it's fine. Like a sound designer for a game knows what they've used in the past, they think they can just use that. In our case, that was bad. Probably in other people's cases, that's great because they can just transfer their skills. But yeah, we left that a bit too late. And the game does have localization. Players can localize their own audio, but we were making a huge amount of content with a huge team, and there's a difference between one person making a game with one translation and an 80-person team making a game with 20 translations and VO in every single language. So with this talk, I kind of just wanted to give an overview of what we did and the challenges that we encountered. And maybe also talk about some neat ideas that other people might find useful in their own projects. But I also want to give some takeaways as well. And the first one is that putting aesthetics before tech design can be a great way to work. You can be sometimes liberated by limitations if they serve this creative flow. It's useful to basically pick an aesthetic and then narrow down what you need in terms of tech for that aesthetic, as opposed to going and picking something up from the shelf and just using something that's very broad, where you have to contend with all the things you don't actually need to use in the UI, and constantly butting up against that. I think also making prototyping live inside the main tool is great because it just cuts down on time and again keeps you in that flow. Integrating tools as much as possible lets developers be more expressive. Like I said, in our system, if an animator encounters an audio bug, they can just fix the audio bug. Like if the audio is a bit out of sync or something, or even if it's too quiet or like something's happened with the sample, an animator who's working on a walk cycle or some facial animation or something can go and just poke that and fix it and publish it. Whereas in other games, they'd have to go probably ask the audio team to open their implementation project in a different tool, and then, yeah. So, and vice versa, like our audio team is quite well versed with animation, so they can happily help with, something being wrong with the way the animation interacts with the audio, for example. Shape and space is a great way to not just visualize, but implement sound. I think it's just fun to try new ways to work, especially if you have to work with a constrained input method. But I think this preset interpolation approach to sound design is a unique way to approach that. I think it lets you treat sound design more like performance. It just makes you think differently. And it's just more fun than fiddling with sliders and knobs and dials. And also, ultimately, that music and audio tech can be fun for a very wide audience if we can find the words and metaphors to popularize it. And I think it's worth thinking here about the fact that music can have a varied hierarchy of parameters. We think of music as normally having rhythm and tempo and harmony and pitch and timbre, but you can make reduced hierarchies of parameters where, hey, you know what, this system makes music that focuses on rhythm and pitch, or this one focuses on timbre and music and movement. So you can think of ways to basically just make it approachable for people to make music by reducing the number of things they need to think about. And that's something we tried to do. In the end, our system is still quite general. It can do all of those things, but because it's rooted in those original prototypes that focused on textural stuff, it just has a certain vibe to it now that really leaks through all the time. So for the future, the tools are now in the community's hands, and we have endless mountains of feedback to go through. It's a bit like in the earlier days when we were still developing the tools, when we had all this constant pressure from the team to add more things. We have to do similar triage and try to combine feedback to get to result in actual useful features that don't result in feature creep. But yeah, we're gonna add audio import. We had audio import at one point back in the early access, but it just needed more work. And eventually, I think it might come back. Audio export will be coming eventually, I hope. I mean, these are just things that are on my mind more than anything. Sample packs definitely coming. Our team can just dish out sample packs continuously, but also the community is making samples, so it's kind of a weird thing where like, what else can we possibly give the community they can't make themselves? OSC support is already in the game. You can drive the game's audio tools with OSC just in terms of playing notes and driving spiciness, that L2 parameter I mentioned earlier. But we are working on some fun stuff for the future. And one thing I've always wanted to try, and I think eventually I'll get a chance to look at this again, is just AI and MIR sort of music analysis. The cool thing is, because our music is all symbolic, it's just a goldmine for just analyzing and generating. So we can make systems that maybe help you compose or help you write or fix your tracks, or recommend music for you based on the actual symbolic data that's there. And one thing I'm really super hyped about is Dreams on a stage as a stage instrument. So we've actually done a couple of concerts with Dreams at game shows, and I've taken Dreams on stage on my own as well. And the thing I really, really like about it is that I can face the audience, and behind me have my actual screen where I'm working, and just show the audience everything that I'm doing. It brings back that missing aspect of kind of laptop performance where you don't know what the artist is doing. With Dreams, I can fully sort of broadcast my process, and it doesn't look like a tool. It almost looks like a game. I can have visuals and stuff in the background behind the actual tools I'm using. a lot for watching this, and please get Dreams and make tons of stuff in it. So yeah, thanks, and I'll be taking questions now.
Yeah, thank you so much for this talk. Can you hear me?
Yeah, we can hear you.
Yeah, thank you so much for this talk. I'm absolutely blown away by this. I've not, seen this before. And, I was just watching your talk, and I have literally on my desk, like one of these things just like lying around just now. And I was kind of imagining, things I could do with like this game. But then unfortunately I'm looking in front of me, and there's like a screen, and there's a door, and there's a bunch of plugins, and I'm pretty much stuck in that paradigm. It feels that we are kind of missing out on a lot of creative tools by being stuck in this world. So, but I'm wondering, is there anything, do you have any plans kind of to port this to other platforms, to like give something to people who are maybe not kind of in this ecosystem of like a console, and more like on the kind of traditional side of things of producing music, like in a DAW?
Hey, can you hear me?
Yep.
Yeah.
Awesome. There's no plan to bring it to any other platforms like Windows or OS X or anything. It's always, for now, it's probably going to be on the PlayStation. But the thing about the PlayStation is it kind of becomes a replacement for your PC in this sense. And I don't think we set out to make an audio workstation. We didn't want to replace Pro Tools for anyone. It's meant to be a separate thing that works a bit differently, that puts you into a different mindset. So that's kind of how I think about it, basically. But for example, we've used it to set up installations where we just, instead of leaving a Mac somewhere, we leave the PS4 and it just runs the game, just visuals and audio and stuff. So I think that's how I think of it, basically. But I mean, you can also, there's no tool in the game to export the audio to a WAV file, but you can easily just share and record your screen and export the audio from that. And in many cases, people like to attach visuals to their music, because doing visuals in Dreams is really fast. So generally, the things you consume within the game are not just pieces of music, but they're more commonly audio-visual experiences, if that makes sense.
Yeah, thanks. That makes a lot of sense. So how can I check this out?
You just have to get a PlayStation and buy it.
All right. Yeah, I already have the PlayStation, so I guess I need to check out the game now.
But I mean, compared to an audio workstation, it's probably a fraction of the price as well. I mean, it's the price of a normal game on a console.
Thank you.
Yeah, so I had a quick question from Alina Almasan. Who actually came up with the original idea for Dreams? How did it actually come into conception?
For the whole game?
Yeah.
I don't think I could tell you. Before this game, we made something called Little Big Planet. And that was a game where similarly you could make anything you wanted. You could make games and even make music. But mainly you can make games. And I think Dreams was just an iteration of that, adding more disciplines, basically, beyond just making games. I couldn't tell you where exactly the idea came from, because I started halfway through the process. Mm-hmm. But I think the team just kind of naturally evolved towards this shape for the game.
Nice. I have one more question as well. What's your background? How long have you been working in audio or in development, and how did you find your way into this particular area of development?
So I came to the UK in 2008 to study music tech, and I went to Bournemouth University, and I did my bachelor's there. Wow. And I did a music tech Master of Arts at York, and then I started doing a PhD for a while, but I quit that. And I think, I just kind of like applied for the job and got it. And during that time, I just did lots of little kind of side projects and stuff that I used to post on my YouTube.
Nice.
But I mean, I'm a musician as well, so for me, programming and music kind of live together in the same part of my mind in a way. Mm-hmm. And I've always liked making tools just to aid myself with music, but also now to aid others, basically.
And there's a question from the chat. What's the size of the audio dev team there?
The audio programming team is just me and Alex Evans, our tech director. So at its largest, it was 2 people. But we have a content team, which includes multiple sound designers and composers. And we have a few people who we outsourced as well. But generally, we do a lot of this stuff in-house.
Amazing. Great. So, yeah, I think it's time for our next talk. Thanks once again, Bogdan, for all your time. This is incredible.
Awesome. Thanks for having me on. Yeah.
Really good stuff. Thank you so much.
And by the way, by the way, before we start our next talk, I should note, yes, apologies for the technical hitches at the start, and that these talks are going to be individually uploaded online as well for people to check out and to watch individually without the technical hitches. Thanks everybody that's joined us for dealing with the logistics and everything, and yeah, we appreciate your patience. Great. Let's jump into the next one, Timur.
Right. So next up is Christian Steinmetz, who is also live here with us. So I think you also pre-recorded the talk, but also will be available live for questions afterwards. So Christian is a master student at Universitat Pompeu Fabra in Barcelona. And he's going to talk to us about his intelligent EQ. And I'm really, really looking forward to that.
Hello, thanks for joining me today. My name is Christian Steinmetz, and I want to talk about my project FlowEQ, which is about using machine learning in MATLAB to build an intelligent EQ plugin. So first, just a little bit of background about myself. Currently, I'm a master's student at Universitat Pompeu Fabra in Barcelona, and I'm studying sound and music computing within the music technology group here. Before that, I did my undergraduate degree at Clemson University, and I did actually 2 bachelors there, one in electrical engineering and one focused on audio technology, so things like mixing, mastering, and live sound. And in addition, I've also worked a few different internships and audio-related things. Currently, I'm working at Dolby Labs as an intern here in Barcelona while I'm doing my master thesis, advised by Joan Seta. Before that, I also worked at Bose and Cirrus Logic. So my background is about building tools for specifically audio engineers for mixing and mastering, things like that. So let's get right into it. So first, let's start a discussion about EQ and just go over some basic ideas and how this ties into the project and the big picture. So as I'm sure you're aware, one of the most popular tools that an audio engineer might use when making a mix or editing dialogue or things like that is the parametric equalizer, which is popular because it's a very powerful tool for shaping the timbre of different recordings. And the parametric EQ is interesting because it features powerful controls that gives the user a lot of ability to tweak and adjust things related to the timbre, the frequency content. And those 3 main controls are first the gain, which allows us to adjust, it's a boost, a cut, how much, things like this. The frequency, the center frequency, where is this filter going to impact frequencies across the spectrum, and the Q control or bandwidth, about how wide or narrow will this frequency adjustment be. And things can start to get very complex when you have more than one band. So here, we're just looking at one band, but as we increase the number of bands, 2 bands, 3 bands, 5 bands, now the complexity of the expressivity of this equalizer is very high. Meaning there's tons of different ways you could set it, right? So for the user, if they are, editing, let's say, a piano, and they recorded a piano that has a certain sound, now they want it to sound in their head, they want it to sound different. The mapping of figuring out which EQ parameters achieve this is quite difficult, and this is what audio engineers study. And they're focused on learning, having the intuition immediately, how do I use this equalizer to achieve the sound I want? But for novice users, musicians or amateur recording engineers, this can be really tough. And the parametric EQ, is difficult to use for this reason. So with this additional control, you get complexity, as is often the case. So this is kind of one of the questions that FlowEQ aims to answer. And now, what is FlowEQ? So FlowEQ aims to provide a simplified control of a parametric EQ by distilling the control of all of the 13 parameters of a 5-band parametric EQ into just 1, 2, or 3 controls that the user can select how many controls they want, And you can see just a demonstration here of the plugin where the user is adjusting one of the sliders here, and you'll see that the transfer function of the parametric EQ is changing in this kind of smooth fashion. And the idea here is that we want the user to use their ears to find the EQ setting they want instead of looking at things like cutoff frequency, gain, etc. And the idea is that it's kind of like a tone control, like the traditional tone control, bass, boost, treble, cut, things like this. But instead of having those simple, shelving filters, you actually have a full 5-band parametric EQ that the user can control with a very limited number of parameters and simply just tweak it till they get the sound they want. And we do this by using a machine learning method known as the disentangled variational autoencoder, or beta VAE. And we'll talk a little bit more about how that works and how it comes into play. So first, let's address the theory here. How are we going to think about this problem and how can we potentially use machine learning to solve it? So first, we need to talk about this concept of something known as the autoencoder. And an autoencoder is comprised of two main functions. The first function is the encoder function. And in our case, the input are the 13 parameters of our parametric EQ. Then this function maps this input to a lower dimensional space in the middle, which we call the latent space. Then the second function is the decoder. And the decoder takes as input this compressed representation, and it tries to reconstruct the original parameters without having all the information there. And we train this just by simply putting in an input and asking it to reconstruct itself. And you may say, well, this isn't very useful. And for example, here's how we plan to use it. Here is the decoder portion of the network here. And you'll see that there's this 2D latent space where we have an X and Y axis, basically. And that means that the encoder, what it's doing during training is mapping every single input to just 2 controls. And then the decoder has to take those 2 controls and try to map them back to all 13 controls as accurately as possible. And this forces this latent space to encode the information as efficiently as possible. And then what we want to do eventually is then have the user select a point in this 2D space. Then this will decode to a unique EQ configuration. Every point will. And if we train this well, this will provide us something useful because we can now use just 2 controls to control all 13 controls. And we go a little bit further because that's kind of just the formulation of what we would call a vanilla autoencoder. But we want to use something called a variational autoencoder, which essentially reformulates this encoder to be probabilistic. And I won't get into the math or the details of this, and you can check out this paper if you're interested in learning more. But it has some really nice features that are useful for us. The one is that it centers these projected points around the origin of this latent space. And this is nice because if we know now if we want to sample points, they're going to be basically centered around the origin. And it also means that similar samples, so EQ curves that are similar to each other, will be placed in the same area of this latent space. And this is of course what we want because we want to move around this latent space, and when we sample, we want them to be some coherent movement that the user can understand. And it also means that the latent space will be densely populated, again, what we want when the user's going to sample from it. And finally, we need to talk about this idea of disentanglement. And disentanglement is pretty simple. It just means that for every dimension within our latent space, that dimension encodes information about some high-level semantic property. So in this little graphic, I've shown that, for example, moving in the positive X direction means that you'll be getting an EQ that sounds more bright in comparison. And this is obviously really useful because now these controls can, if they're disentangled, now contain some sort of higher-level information. But the question is, how do we achieve this disentanglement? Because by default, this doesn't happen. And the answer is we adjust the loss function. And again, don't worry about the math here. You can check out the paper if you're interested in the details. But in this paper, they introduced something called the beta VAE to test out this disentanglement idea. Like, how can we enforce disentanglement while training the model? And it's very simple. They find that just by adding this beta in the loss function, which is just a scalar, just one value you can tune, what this does is actually weigh these 2 different loss terms differently. And changing this changes the representation we learn. And the simple takeaway is that a larger beta means greater disentanglement. And we'll see how that comes into play for our actual implementation here. So now let's talk about the actual model, how it's implemented, and how does this actually work. So the model architecture was designed to be purposefully simple. It's very small. It's by no means a deep neural network or anything like that. It's just a very simple neural network composed. You can see here the architecture, one dense layer for the encoder, and then a nonlinearity ReLU, and then we have latent space, which is our mu and sigma, that's the distribution that's being predicted. Then we also have the decoder in the same way with a nonlinearity, and then an output layer that maps that down to 13 dimensions of the output, and then a sigmoid to make all of our outputs be bounded between 0 and 1. And there's a few reasons for having this super simple design. I mean, the first is that we want it to be really fast because this is going to be used in a real-time plugin. So we don't want the user to have to move a knob, and wait 3 seconds before they can hear something. So now in this formulation, they can move the sliders back and forth and there's no delay. And it also means that implementation in MATLAB is easier because a lot of the newer layers that you may want to use in a deep neural network aren't fully supported yet, because I actually had to implement this myself in MATLAB for it to work. And the final reason is that our data has low dimensionality. We're not dealing with images or raw audio here, so we can get away with a small network and it still works. And obviously for any machine learning project, we're gonna need data to learn something useful, right? So in this case, we're using something called the SafeDB dataset, which is a really interesting dataset. And they basically, in this project, they built an equalizer, they gave it to a bunch of users and said, create EQ presets for your mixes that you're using, like on different sources, guitars, bass, etc. And what they found was that you could get all of these different EQ curves, right? And what I'm trying to do then is, what I'm saying is that these EQ curves are useful portions of the full search space of the EQ, because we know that there's many ways to configure it, but some are more used than others. So this data set gives us a way to kind of say, these are the points we care about. Now let the model learn how to structure them in a useful way. Now, some details about the training. So the first interesting thing is that we actually train 12 different models. And in each model, we adjust something a little bit to see how it affects the performance of the model. So we train with 3 different latent dimensions, 1D, 2D, 3D, and this controls how many parameters there are that the user controls. So in the 1D case, the user has 1 knob, and that controls all 13 knobs at the same time, and you see the pattern. And we also train with different values of beta, and this means we can observe how increasing beta changes the disentanglement. And we'll see more on that in a second. This is kind of a basic machine learning pipeline. We use Keras, so all the training is done in Python. We save out the weight so that they could be loaded in MATLAB, atom optimizer, learning rate of 0.001. We train all the models for 200 epochs, and this whole process takes less than 2 hours on CPU, so very fast. Now here is the latent space that I was talking about. So this is for one particular model and with a beta of 0. And what we do is we create a plot like this to kind of get an idea of the structure of the latent space of this particular model. And what we do is we take the XY coordinates of the latent space and we sample from them, and at each point we decode that and turn it into an EQ parameter. And you can see the transfer functions here. And now you'll see that as we change the beta, the EQ settings, the structure of this latent space changes. And basically what we're looking for is we want the best structure that lets users find the EQ setting they're looking for the fastest. So, like, see what happens here. And you can see when we get to this point, now it's much more structured. It's very smooth as we move from one point to the other. And this is good. We want good continuity between the different parts of the latent space. And you can see actually what happens is if we go higher, now things become so much the same that if you look now, the x-axis has been completely removed from usefulness, and that if you look in the center and you move from left to right, there's no difference in the EQ. So now the x dimension has been completely forgotten, and this is what happens as you increase disentanglement too far, because now what it does is it's actually only using the y axis to encode information. So really what we would want is to end up using something like this one back here, and maybe this is the best. But in the plugin, we actually include all of these so you can listen to them. And now let's talk about the actual plugin implementation. How do we take the model and put it into MATLAB and make a plugin and actually make it, have a real-time machine learning that we can use for some sort of application? So like I said, we use the MATLAB audio toolbox to do this. It has a really nice framework for, you have a process function, a setup function. You can put MATLAB code in there and turn it into a VST plugin. So that's nice. In the plugin, there's 3 modes of operation that I've defined: these traverse, semantic, and manual. I'll talk about that more in a second. And again, the user has control over these 12 different models. They can choose which one they want to listen to, basically. And they all have different representations. And there are some there's some workflow I had to do to get this machine learning model to actually work in the Auto2 box. And like I said, the first thing we do all the training in Python. The workflows and the libraries, in my opinion, are a bit better working in something like Keras or PyTorch, and then transferring to MATLAB or Juice if you want to actually do the implementation. So we save out the weights first. Then I have a MATLAB function that converts these to map files in the format that my classes they understand. Then, like I said, I also implement the model architecture in pure MATLAB code. So doing the matrix operations of the neural network, I implemented in MATLAB so that they could be compiled into the VST plugin. Then there's also some UI controls that basically control swapping out these weights in real time in the plugin, so that we can have the same exact model architecture, flip the weights, and now we're using a different model basically. And the final step is basically implementing a 5-band parametric EQ in MATLAB. So this is me just creating 5 biquad filters using the basic, parametric EQ thing. So there's a low shelf, 3 bandpass filters, and the peaking filters, and then a high shelf filter. And so we connect those EQ parameters that the model's predicting directly to those coefficient generations, and then that coefficient generation process. And then we have this plugin running in real time to do the actual EQing, right? And here's what the final EQ plugin looks like with the full-blown interface with all of the elements. And I'll just walk through some of the elements here so we can understand. So in the traverse mode, you'll be doing the latent space traversal that I mentioned. And this is where you have those X, Y, Z controls. And this is kind of the main way you use the plugin to sample. But there's some other modes too. So there's also this semantic mode, which what it does is I've kind of pre-chosen different points in the latent space for each model that I think are warm, bright, or different things like this. And then what you can do is actually sample, interpolate between those 2 points. So you pick 2 points in the space, move between them, and you get some EQ that's somewhere between those 2. And you can pick whichever direction you want. That's kind of interesting. In the future, I'd like it so you could have the user pick 1 point and another point that they want arbitrarily and move between them. But currently wasn't able to implement that with the current MATLAB framework. And finally, there's the manual mode. So you see here the original controls of the EQ. Now, how I envisioned this originally working is that moving the X, Y, Z controls of the plugin would change these knobs in real time. But unfortunately, the MATLAB didn't allow me to do this either.
I think I did something wrong here. Sorry, I'm just having some difficulties over here.
But there's some other modes too. So there's also this semantic mode, which what it does is I've kind of pre-chosen different points in the latent space for each model that I think are warm, bright, or different things like this. And then what you can do is actually sample, interpolate between those 2 points. So you pick 2 points in the space, move between them, and you get some EQ that's somewhere between those 2. And you can pick whichever direction you want. That's kind of interesting. In the future, I'd like it so you could have the user pick 1 point and another point that they want arbitrarily and move between them. But currently wasn't able to implement that with the current MATLAB framework. And finally, there's the manual mode. So you see here the original controls of the EQ. Now, how I envisioned this originally working is that moving the X, Y, Z controls of the plugin would change these knobs in real time. But unfortunately, the MATLAB didn't allow me to do this either. So I'm looking to potentially have this working in a Juice version where you would actually see this. And then the idea is you kind of do the coarse control with those XYZ sliders, and when you get very close to the EQ you want, you can tweak a little bit with the manual mode. And then here's where you actually control the model, choosing the latent dimensions, the beta that we talked about, and all of this. And then there's also finally an automatic gain compensation, which helps because since you're changing these EQs so drastically, the overall level can adjust a lot in real time. So this tries to keep the level constant when you're listening, so that you can hear the timbre change more clearly. And also there's a light version, because the whole point of this, right, is to create a simple version for novice users. They don't want to have all this clutter. So the main plugin I just showed was kind of demonstrating all the possibilities, and it was also a way to do the testing ground of listening to different models. So in FlowEQ Lite, it's the stripped down interface that's got just these 3 XYZ controls and one model that I picked as the best. And this is meant towards those novice users that just want to kind of almost look at it like an Instagram filter, where you can just move these sliders back and forth until you hear what you're happy with. That's the idea. And also there's a demo of this on YouTube. I won't play it now, but you can check it out if you want to hear the plugin in action and kind of get some more explanation of how it might actually be used. But that kind of concludes everything I wanted to talk about today. Thank you so much for coming and listening. I encourage you, if you want to know more about the math, like how this works, the implementation details, please check out the project website. Also, all of the code is public available on GitHub, including the Python and the MATLAB code. And there's also additionally, if you don't have MATLAB, you can't build the plugin. I already have builds for Mac OS and Windows 10, so you can also just download those VSTs and try them out as well if you're interested. Thanks again, and hope you enjoyed this.
Wow, thanks a lot, Christian, for that talk. Can you hear us, Christian?
Yes, thank you. Yes, thanks for having me.
Yeah, very interesting. We had a couple questions from the chat. If you could, the first question is, have you explored conditional VAEs in addition to VAEs?
Yes, I didn't include that in this part of the work because there are some challenges with having that be part of the real-time aspect. So something that, like the obvious idea would, maybe just extract some features from the audio signal that you're trying to process and then use those features about the audio to condition the VAE, for example. But the problem is you need to then do this feature extraction and additionally make your model bigger, all in real time, if you're trying to process something. So, and then you have this problem where if your signal fluctuates over time, now your EQ conditioning fluctuates over time. So I found that it was kind of just a cleaner way to use just a simple VAE here for the plugin, but I think there could be some interesting applications for the conditional VAE.
Okay. We also have a question. Will it be possible to use a .wave or other audio formats to give the AI algorithm a sample of what an instrument to sounds like, or is it still tweaking the EQ controls?
Yeah, I mean, that's a great question, and I think that's where we would eventually want to go. But the problem is we actually need more data to be able to train a model that would do this kind of thing, and we just don't have data of this kind right now to do something like this, unfortunately. And in my master thesis, I'm actually working on some elements of this, so maybe we will see some results there.
Great. And we have one more question from Anthony Nichols. Given this is part about using ears rather than eyes, were the training samples made by people who switched off the UI originally? People tend to overuse EQ, and it would be a shame if it was.
Yeah, I agree with that sentiment, but our viewpoint is a little bit different here because the data that the data we're using here was collected in a totally different environment than this environment, and they were specifically targeting professional engineers to collect these, so we kind of are trusting that their choices were good, that the professional engineer isn't being fooled by their eyes, hopefully.
Yeah. We have another question. Says really interesting talk. I'm not sure if I understand this question. What happens with higher dimensional latent space?
Sure. Yeah, so as you increase the dimensions of the latent space, you get more degrees of freedom. So you then potentially get your latent space can represent more interesting or more complex relationships among the input features. So it means you would get more sliders to control, and you would potentially have more fine-grained control, but the trade-off there is we want to keep this simple. So I chose 1, 2, and 3 because this gives the user a lot of flexibility about how much control they want, and it's also easy to visualize.
Okay. Did you have any user testing for the EQ, and did you get any feedback from them?
Yeah, only informal user testing. I would like to continuing this work would be to do a more formal evaluation of the plugin, but in the limited testing I did, there was some interesting feedback as far as I think the real application for this, like I said, would be in either novice users, like just musicians, people that don't want to get into the nitty gritty, or maybe for some sort of mastering kinds of applications or even when the users, like something cool that someone mentioned was that you could see this being an option on something like Spotify, maybe where you want the users just to be able to adjust control, but not have to know everything about an EQ, for example.
Great. And we have another question. How does this compare to Sonable Smart EQ?
I can't say that I'm familiar enough with it to compare.
Okay, great. Okay, it looks like that's all the questions from our chat. And once again, thanks for everybody tuning in. We've had so many people that have been joining us. A lot of familiar faces. Any comments, Teamer, from your side?
Yeah, this is really interesting. Thank you so much. I don't know. Like, are we going to move on, or is there any more?
Yeah. So I think we're done with the questions. I think we're ready to move on to the next talk. And,
right. So thank you so much, Christian, for this talk.
Thank you for having me.
Yeah. The next one is our last talk for the evening, and I think it's kind of a significant event for the music industry. It's about MIDI 2.0, and so MIDI has been around for like 4 decades now, and I've used it both as a user and as a developer. Worked around some of its shortcomings, and then we had MPE, which I worked on. I wrote like a Juice implementation for it, and then we had MIDI HD, and I kind of looked at various of these things over the years, and like it always seemed to me that it's kind of challenging to cram all this information that you want to be able to use musically in those like 7-bit messages. But now MIDI 2.0 is out, and I'm like really excited to see where that's going to take us. And Josh, do you want to introduce the next speaker?
Yes. So Brett Porter is a lead engineer for audio and music projects at Art and Logic, which is a custom software development consultancy in the U.S. For the past few years, he's been a member of the MIDI Manufacturers Association Prototyping and Test Working Group as the MIDI 2.0 specification was in its final stages of its development. He holds degrees in composition and electronic computer music from the Frost School of Music at the University of Miami, and he's also an active trombonist. So please welcome Brett. Share my screen again. And here we go. Let's not hit any buttons this time.
Okay, so let's look at MIDI 2.0. Why am I here? A couple years ago, my colleagues and I at Art and Logic were approached by the MIDI Manufacturers Association, who were getting ready, after many years of talking about upgrades to MIDI, developing a standard that they were ready to unleash on the world. And we're interested in having us work with them on doing some prototyping of that spec as it was being developed, which is a pretty cool thing to be involved in. And so I had kind of a front seat to the tail end of upgrading a 37-year-old ubiquitous standard that we hope was going to be wildly popular in the rest of the world. So look back quickly at MIDI 1. It's been around forever, and most of you already know all of this already. But anyway, MIDI 1, which was originally released to the world in the early 80s, 1983 at the NAMM show, was a byte stream. It was designed to run on very low-powered CPUs and microprocessors of the time over copper wire pairs, running short distances at relatively slow speeds. So it's a byte stream. Each message inside of MIDI is either 2 or 3 bytes long to conserve space. You don't want to use any more bits than you have to use. Most of the messages in the format were restricted to only having 7 bits of data. So a maximum range of 0 to 127 of expressivity. The pitch bend gets big, 14 bits of resolution from -8K to +8K. Any one cable can carry 16 channels of MIDI data over it. And as we said, it was pretty slow, but fast by the standards of the early 80s at 31.25 kbits per second. But in a gigabit Ethernet world, it's faster to walk there than it is to send a MIDI message. Sometimes it feels like. And these 7 MIDI messages were defined in 1983 as part of the spec. So these are basically the operations you can perform over MIDI. You can send a note on, you can send a note off. send a pressure message after notes are playing to everything on that channel. You can bend the pitch. Again, all notes on that channel will receive the same bend data. You can change the program or patch number that you're playing right now. There's a polyphonic pressure message, which would allow you to have different pressure data going out in each key, but for a bunch of reasons it ended up not being very widely used. And control change, so anything from sustain pedal to filter cutoff, anything that you can send to control the sound as it's playing is a control change. There are other messages in there as well, system exclusive you've probably run into for patch editors and getting things set up, and channel and system common messages for other applications. And in the couple of decades that we've been using this, a bunch of myths have founded around MIDI. Nobody uses it anymore. I've talked to a lot of people since we've been involved in this who believe I don't use MIDI. All my keyboards now use USB, and they're not thinking that it's MIDI data that just happens to be going over the USB cable. There are people who think that nobody uses MIDI because everybody's using OSC, and a lot of people do use OSC, and where it's useful, it's great, but it has not replaced the need for MIDI. And there are people that have bought MPE-related gear, which we'll talk about a little later, that think MPE is all you need now, but it's really an enhancement on MIDI and exists strictly in terms of MIDI. We've also heard a lot of complaints over the years about MIDI. It's too slow. The timing is really sloppy at the events. The controller resolution is too slow. 7-bit data is not great. There aren't enough channels. 16 channels of data for a really complex piece of music is not adequate. And it can also be really hard to get things working together. And the one thing all of these complaints have in common is that they're all excellent points. And the companies that have been making MIDI gear have heard all of these for 30 years, probably since a month or two after the standard was published in '83. On the other hand, it still makes a lot of sense as a manufacturer to build MIDI into your equipment because it's ubiquitous, it's installed in everything, it's not very expensive or complicated to implement, and as a result, it just keeps building on itself. There's not a lot of worry about your product becoming outdated because you put MIDI on it. I can go into my closet, pull out something from 30 years ago, plug it into my brand new MacBook, and everything is still just going to work. And I don't have a lot of technical things in my life where you can say that. So what happens next? If you want to upgrade and modernize something that's been used in every kind of musical context in the last 35 years, but not break any of that things, what do you do? How do you go about that? So there were 3 rules that were followed when developing MIDI 2. One is obviously pay attention to fixing and reducing all those things that people have been complaining about. 2, don't break anything. Causing people to need to throw away their beloved old gear would be a really, really bad thing. And the 3rd rule was to take what MIDI does well and make it even more so. The things that make sense about it, and most of it does make sense, can just be extended and enhanced and made better. So how did we change that and make MIDI 2.0? And the first question everybody asks me is, do we get a new connector? There are still a lot of people that when you say MIDI, they think of that 5-pin DIN on the back of their DX7. And yeah, originally the physical connector and electrical protocol was as much an important part of the standard as the data protocol. But over the ensuing years, MIDI's become really comfortable running on basically any kind of transport, from 5-pin DIN to Bluetooth to USB to Ethernet. So what are we going to do? How are we going to go about this? So what we wanted to do was build in a couple different things. One, new capabilities that are going to make MIDI easier for end users to use. For instance, devices will be able to automatically configure themselves to adapt to whatever they happen to be plugged into on the other end. And things that make MIDI better to use. And you could say that anything that makes it easier to use makes it better to use, but for the purposes of this, new capabilities that are going to make it better to use on stage and in the studio once everything is connected and talking to each other. And probably the most important part of that is that, unlike MIDI 1, which is strictly a one-way protocol, MIDI 2 requires two-way transmissions. When you plug 2 pieces of MIDI 1 equipment together, nobody knows what's at the other end of the connection, or even if there is anything over there. And for simple systems, that's really fine. But as you start to add more complexity into your system, it becomes really useful to have a way to make that a closed-loop system. At the very least, when you plug your controller keyboard into a rack mount synth, it'd be nice to be able to display the name of the current patch on the keyboard instead of having to need to remember while you're sitting there that patch 34 means electric piano, or have to walk across the room and look at the synth to find out what sound is going to come out. Most of the new capabilities that have been added only work because connected devices will be able to ask each other what the other one knows how to do. And we've gotten used to this every place else we touch computers. There was a time when connecting a new printer was really a hassle and an all-afternoon job. And now you just plug things together by USB, they figure out what they are, and everything just usually kind of works. And the way that this has been added into MIDI is a system called MIDI CI, MIDI Capability Inquiry. And essentially everything in MIDI 2 relies on this set of operations. And this is where we need two-directional communications. When a piece of MIDI 2 gear is powered up, the first thing that it does is enter a process of discovery. There may be an auto-config button on gear at some point where it goes out and queries what's out there, who can I talk to, and what do you know how to do. Once MIDI CI is in the picture, then you build what we call the 3 Ps on top of that. So the first of the 3 Ps is property exchange, where two devices can talk to each other and say, what do you know how to do? What kinds of parameters do you have? What kinds of things do you support operationally? And the second of the 2 Ps is profiles, which is a way to automate and make simpler configuration of devices talking to each other over MIDI. And then the third of the 3 Ps is protocol negotiation, which is what kind of MIDI do you speak? So since we're upgrading everything, we're going to talk in a bit about upgraded the data protocol underlying all of MIDI and some of the cool things that lets us do. Okay, so property exchange, which is really the backbone of capability inquiry. The nice thing about property exchange is that it happens over plain old existing MIDI 7-bit system exclusive messages. It's going to be really easy for manufacturers to implement this. And instead of dealing with binary data like most MIDI development is, the decision was made when building property exchange. We're actually setting around human-readable text that's encoded in JSON structures, which if you've done any web development in the last 5-10 years, you've worked with, it's sensible, and it's going to be really easy to build a lot of these capabilities into both hardware and software by people that may be not as comfortable going down and shifting bits around and dealing with things at that level. The MIDI 2 standard defines a set of what they call foundational resources that property exchange devices need to implement. And the basic foundational properties you're going to find on everything soon, device info, which is a way for a piece of equipment to explain what it is. What is my name? What's my software version number? Who made me? What's my serial number even? So if you have a couple of different of the same device on your network, you'll be able to identify them unambiguously. What are the channels that a device supports? What kind of modes? If for instance, you have a piece of gear that supports a song mode and a loop mode, it's nice to be able to know that over the wire. And also to be able to just, if nothing else, get the program list that's on a rack mount synth back. I mean, anybody that's used a VST plugin is used to having all that data right there all the time and have it be able to be recalled by name. Finally, that capability comes to regular standalone MIDI gear. Another cool thing about properties is that properties are kind of rich. You can get any property, obviously. Many properties can be set over the wire. And the new thing that's going to be kind of interesting is the idea of being able to subscribe to a property, which will let you do things, again, because we're bidirectional. Consider the case where you've got a controller plugged into a rack mount synth. Right now, if you press patch change on the keyboard, it's not surprising to be able to change the patch over on the rack mount synth. But what would be surprising, and something you could do, for instance, by subscribing to a property, is to have somebody change the patch on the rack mount synth and have that change be propagated back to the controller keyboard so that you always know what's going on both ends of that. Profiles, which again is auto configuration. And if you've ever used general MIDI, you already get the basic idea behind a MIDI 2 profile. Any general MIDI device has a well-defined set of preset sounds, specific program numbers. You know that it's going to be able to receive on all 16 channels. You know that channel 10 is going to be the drums. A profile is really just a set of rules for how a receiving device that implements that profile has to respond to a chosen set of MIDI messages. And this is going to permit a tighter and more flexible integration of controllers on MIDI receiving devices. So basically 3 families of profiles. There's feature profiles, instrument profiles, and then profiles for effect devices. And feature profiles are things like general MIDI, show control, note tuning. MPE is a feature profile, or will be a feature profile. Instrument profiles lets you define things like how orchestral strings would behave, or piano, or organ. And effect device profiles are exactly what you'd think, having a common set of controls that interact with a family or flavor of device. The easy question to ask about this one is, who cares? We've gone without this for a long time, and we're okay, right? And here's an example of why this is going to be something interesting. Consider the case of a Hammond drawbar organ. Everybody's seen these, and they're all the same. They've all got a keyboard. They've all got these 9 drawbars for controlling the timbre of the sound, and usually a control for a rotary Leslie speaker. Each of those drawbar controls needs to be able to send out MIDI controller data. The problem is there's no standard for this. Everybody who manufactures a drawbar controller or a synth that responds to those is free to do whatever they want there. And there are even manufacturers that have multiple products that are not compatible within their own product family. So using MIDI CI and profiles, we can now define a drawbar organ profile and have everybody that implements it just plug together, agree that they're going to use the drawbar organ profile on a patch, and it just works. Or hypothetically, looking into the future, orchestral articulation. So if you've used a sample library any time in the last few years, you're used to the convention where the bottom octave or so of your keyboard are used as key switches. So you can have one of those notes set so that the notes you play with your other hand are going to be pizzicato or legato. Right now, there's no better way to solve that. But with MIDI 2.0, we can have that built in and have it standardized, and with note attributes, which we'll look at in a few minutes, have that all built in to the controller itself, rather than requiring this kind of out-of-band special interpretation of MIDI events to affect other MIDI events. Similarly, you could have attributes that control open versus muted brass sounds or percussion techniques. And the third of the 3 Ps is protocol negotiation. So once 2 devices talk to each other and start to ask, what do you know how to do, they can choose to move into the new MIDI 2.0 data protocol, which is a system that we call universal MIDI packets. And whereas in MIDI 1, if you remember, it was a byte stream. It was the data kind of defined its own boundaries through some low-level bit level trickery. Whereas in MIDI 2, everything is a packet. Everything is, all the data that goes across a MIDI 2 communication channel is one of these 4 sizes of universal MIDI packets, either 4, 16, or up to 128 bits long, depending on the data that's carried inside of it. And this lets us use the bandwidth a lot more flexibly. It lets us use the bandwidth a lot more efficiently. And it even lets us do cool things like sneak MIDI 1 messages inside of a MIDI 2 universal MIDI packet. Something we get for free with this is one of the original complaints about MIDI that we've heard for so long is the idea that 16 channels is not enough. So MIDI 2 universal MIDI packets not only have channels, but they also have 16 groups. So if you look at the first 8 bits of every universal MIDI packet, there are 4 bits that tell you what type of message you're looking at. And there are 16 possible message types within UMP. And then what group does that message belong to? So there are 16 groups, and each group can have 16 channels inside of it. So that upgrades us from 16 to 256 potential MIDI channels worth of data on one physical transport. And that's what I just said. One other thing that was added with MIDI to UMP, one of the message types is MIDI to timestamps or jitter reduction. And there are a couple different methods used for this, and this is an optional thing. You don't have to use this. But if you do choose to use, and when I say if you choose, if the sender and receiver agree that they're going to start using jitter reduction timestamps, that will prepend a one chunk size UMP message to the beginning of every MIDI data message that timestamps it down to a few microseconds, 32 microseconds. And this is really useful in cases like when you're recording into a DAW, where consider MIDI 1, it was all serial stream of bytes. You hold down a large chord, you use all 10 fingers on your keyboard, and there's going to be a noticeable difference in the time between when the first MIDI event hits the synth and when the last MIDI event from your 10th finger hits that synth. If you're using timestamps, each one of those node-on events is going to have the exact moment that the key was pressed down prepended, which means that when the DAW receives it, it can log the event as happening at that recorded time rather than when it received it off of the wire. So MIDI timing is going to get a lot better. We've added a bunch of new protocol messages, and the key here is, A, we wanted to maintain compatibility with old MIDI messages, but we also wanted to make use of increased resolution that we can have because we're on a much higher bandwidth channel now. We also wanted compatibility heterogeneously in the same MIDI 1 and MIDI 2 network. So all MIDI 2 devices are going to wake up as a MIDI 1 device. So what that means is if you don't have any other MIDI 2 devices out there, your MIDI 2 keyboard that you buy next year is still going to be very happy to talk to your MIDI 1 gear as if nothing was wrong. Any MIDI 1 message from an existing device can be translated and possibly upscaled into a MIDI 2 message. Most or many of the MIDI 2 messages can translate back to MIDI 1, and MIDI 1 messages can travel inside of UMP, and that may not make much sense until you remember the idea of JR timestamps, which means that now you can take an existing MIDI 1 device, put a timestamp on it, and instantly increase its timing resolution, which is a pretty cool thing to be able to do. Now, again, in MIDI 1, the maximum resolution on most of your messages was 7 bits, 0 to 127, or 14 bits on pitch bend. In MIDI 2, we blow that up. So velocity on node on and node off goes up to 64K. And all of our controllers go from 127 steps of resolution up to 4 billion. So it's 32-bit control space now, which is going to allow us to build a lot more expressive systems. And with the new protocol messages, the counterparts to MIDI 1 messages all get improvements. Some of the MIDI 1 messages that are upscaled into MIDI 2 get new capabilities as well. And we added also some brand new messages to the standard. So under MIDI 2, node on and node off, the velocity goes from 7 bits of resolution up to 16 bits of resolution. And we add something new, which is a 16-bit note attribute. And there are a couple of those that are preset. Manufacturers can actually use this 16-bit attribute word for whatever they want. But on top of that, a profile can define any special usage that it wants to have for this attribute. So like we were talking earlier about orchestral profiles, being able to control the articulation data within the node on event is going to allow a lot richer kind of musical experience because each note can have its own articulation. You can also carry microtonal data with every node on and node off message. So the 16 bits of note attribute on a node on or node off can be encoded so that it's a 7.9 fixed point pitch message. So that top 7 bits would be essentially the MIDI note number, and then the next 9 bits, which is basically 1/512th of a semitone of microtonal data to apply at the time of node on. So anybody who's done microtonal or Zen harmonic music and has gotten into the practice of having to set up tuning tables, which is not a lot of fun, to do that kind of work, Now, not only do you not have to worry about tuning tables, but again, each note in your piece can have a completely separate tuning unrelated to what it did a measure ago or a beat ago or however long ago. Program change is like MIDI1 program change, except if you wanted to select patches from a different bank on the synth than the one you're currently on, you had to send out a couple of MIDI control messages ahead of time to get the bank set up. That's all integrated into one atomic program change message now, so it simplifies that. Channel pressure aftertouch, again, goes from 7 to 32-bit. Control change goes from 7 to 32-bit. Pitch bend goes from 14 to 32-bit. And we also added some new messages to MIDI2, which add more expressivity to what you're able to do. We have standalone messages for registered and assignable controllers, which you may have run into under MIDI1 under the names RPN and NRPN. The nice thing about the MIDI2 version, again, it's a single message. Using RPNs and NRPNs under MIDI1 required you to kind of go through a song and dance about send out some control changes to set up the RPN or NRPN that you want to be able to send a new control setting to, then send the control setting. You don't have to do that anymore. It's just a single message with 16K worth of controller numbers, 32-bit MIDI2 data, and there's also a new relative control version, which is going to be useful if you're a hardware manufacturer that does something where your controllers are optical shaft encoders, and you just want to be able to say, I want to add one. I don't care where you are now. Go up one. That is just part of the standard now. Also new in MIDI2 is a lot of the per note controls that we added MPE for are baked right into MIDI2. So here's an MPE synth, the Rolly Seaboard. Enough of that. So MPE, MIDI polyphonic expression, is a convention of usages of MIDI1 messages. And the way that it does that is instead of having polyphony on a channel, each MIDI channel only carries data for one note. And on that channel, you can affect the pitch bend independently of the others and any of the controller data on that note. And you rotate through the channels sequentially so that things don't overlap. The problem with this, obviously, is it requires explicit support at each end. Not only does your controller have to know how to generate MPE compliant data, the synth needs to know that that's what you're sending it, and so it can respond appropriately. MPE controllers all have high-resolution multi-touch sensors where each finger is tracked separately, things like velocity and pressure, and in a lot of cases, the actual X-Y location on a key, other parameters as well, but they only work with MPE-aware synths. Whereas, under MIDI2, these per note messages, if you use note on and off messages with that 7.9 pitch attribute, you can have essentially 128 notes worth of polyphony on a per note basis, with per note pitch bend on all of those notes, per note pressure and aftertouch, per note controller data. And unlike MPE, these messages should work on any MIDI2 synth, with the full MIDI2 controller resolution and at a completely high polyphony. That's it for the protocol. The initial thing you're going to ask, at some point a project is going to land on your desk and you're going to say, well, how do I do this? How do I make use of this? Especially right now when there are not instruments and operating system support. So part of the thing that I've been involved in for the last couple of years was working on a tool called MIDI2 Sculpt, which is a debugging and generator tool that can be used to create any of the MIDI2 channel voice messages. It can receive and display in a human readable format any of these messages. And it also has a very rudimentary kind of sequencer, so you can, on a repeating basis, send the exact same MIDI2 message traffic to for instance, if you're developing a synth, this is how you can verify that what it's generating sound-wise is what it should be generating, protocol message-wise. And this is a look at the receive view, where it's showing both three things. It's showing the raw message that came in as a hex data. It's showing a human readable version of that message, so you can verify that you're sending what you think you're sending. And if there are any errors in what you're sending on the wire, this will outline them in red, which is kind of a handy thing to make sure you're not gunking up somebody else's synth. Another tool that's been developed by Andrew Mee, who's a consultant working for Yamaha, is a MIDI workbench that's designed to help debug and visualize MIDI CI, which is going to be a new enough idea for a lot of manufacturers that it's going to take a while to get our head around it, and any kind of tool like this that's going to help you visualize the messages on the wire is going to be a great thing. If you'd like a copy of the spec, or you'd like copies of these tools, if you are with a corporation that is not a member of the MIDI Manufacturers Association, please contact whoever makes these decisions in your company and say, we've got to join. If nothing else, this gets you an inside view into all the standards development. Always looking for volunteers to work on working groups to help drive things forward, and also have a voice in how things go. It's easy to complain. It's not as easy to actually be on the other end making stuff work. If that's not feasible for you, or you're not a corporation, there's also the MIDI Association, which is an end user organization that's run by the MIDI Manufacturers Association and maintains a forum, and this is where all the spec documents are available. So if you go to MIDI.org, give them your email address, they will set you up with an account, and you can download 100% of the MIDI specs and find out everything that I did not go into in this whirlwind tour of the high-level view of MIDI 2. So let's throw it to questions. Thanks.
Well, thank you so much, Brett, for this talk and taking the time.
Hey, yeah, that's very weird to hear yourself talk without... I remember saying that.
Thanks, Brett, for this really great talk. Can I ask a question?
Yeah.
So I'm just wondering, like, I don't know, this reminds me a little bit of what we do in the C++ committee, where we have, new features, but also we can't break all the old stuff, and then we come up with all these new features. I talk about them, and then people ask me, yeah, when are the compilers going to support this? And I think this is kind of a bit similar, where you have all these new features, you have the new resolution, you have all these tools, and this is really exciting. But then a lot of developers, they write against, if you're on a Mac, something like or MIDI, or on Windows, you have one of those numerous like semi-deprecated APIs you're going to be talking to, or like a lot of people use something like Juice, or maybe they have like an in-house version of that, and then you just have some like MIDI message class that just handles that. And my question is, do you have any idea when those people, like the regular kind of developer in the trenches, will be able to benefit from all this increased resolution and these new message types, and actually use it in like actual like production like apps?
Or as I like to say, use it in anger. There's a couple things that have to happen between here and there. Right now, there's no transport mechanism for MIDI 2 data. A proposal has been submitted to the USBIF, which is the organization that maintains the USB specs. Once that's done, then we can start sending MIDI UMP packets over USB. And once that happens, then companies that make things like I/O boxes that need to be able to put USB data to serialize over that channel can start working on their drivers. So once the drivers are ready, then the OS vendors can start building out and deploying their APIs. Neither Microsoft nor Apple are willing to say anything about what they have planned here. So when they make it available, we're all going to find out at the same time, I fear. And then at that point, companies like the Juice guys can start to build MIDI 2 interface stuff into their APIs. I would love it if by the time of next NAMM show in January, if there is a NAMM show next January, that there's something shipping more than what there is right now. As of right now, Roland has one keyboard that they're claiming is MIDI 2 ready. If you ask them what that means, they won't really tell you a straight answer. And Florian Boemers, who makes the Bohm box, has been a member of the working group working on this, and he's ready to roll as soon as USB supports this, as far as I know. So soon, but not today.
Yeah, thanks. That's interesting because obviously, like, I work at a company, we have like an in-house library that does stuff, and I could theoretically start using it, but then obviously I'm talking to the APIs of the operating systems, so I have to wait for them, and I guess the juice guys have to wait for them, and everyone has to wait for them. So
it's frustrating. In fact,
multi-stage process, right? And then
the tool that I wrote, the way that we decided to do this for prototyping purposes, there's actually a secret hack where we tunnel the messages through sysax.
Yeah, because that was a juice tool, right?
Exactly. So that's just it's bundling UMP messages inside of a sysax package and sending it over straight old MIDI 1, which we don't want real people using because it's long-term a dumb way to do it. But as of 2 years ago, it was the only way to do it.
Yeah. Well, thank you so much for all this amazing work, and I hope that all this stuff happens soon and we actually get to use it. So yeah.
I hope so too. People start buying gear. That's.
Yeah. So we have a couple questions from the chat. Scott Hawley says, Brett, are there any other exciting software efforts you're involved in that are almost ready for release that developers in this group might be interested in contributing to?
As a matter of fact, there is. Thank you, Dr. Hawley. I'm posting a link to it in the chat right now. We've been working with Scott Hawley. For those of you who don't know him, he's a professor at Belmont University down in Nashville, and has been doing some really interesting work identifying sounds using machine learning techniques. We developed a project with him that's just gone live on GitHub. You can get the source for this, called Vibrary, which is a end-user trainable sound machine learning recognizer. Hello, Popper.
This is Toast, by the way. Software development training.
I don't know if you can hear, my dog is on the other side of the door barking to be let in right now. So that's Casper outside my door. But anyway, the link that I just posted there, artandlogic.com/vibrary, you can read up a little bit about that. And if they listen to me, it should have a link to the GitHub repo where all the code is.
Great. Okay, so we have another question. Are there any plans or talks about reducing the latency of MIDI over internet for real-time remote performances? I know that's a near impossible task, but I'm just curious.
Well, as was said in the chat, there's a couple different parts to that, and one is the overall actual latency, which is a matter of transmission speeds. You can't go faster than light or faster than Cisco made their router work, so you're limited there. But being able to put timestamps on MIDI messages is going to improve things a lot, at least in instances where you're going to be recording the data. So if your data is going to be looking at timestamp data that it happens to receive at crazy times, it's going to be able to reassemble them at the time that the event was generated. So for live throughput, maybe not. In fact, for live throughput, that may make things a little bit worse, but for recorded instances, it's going to make things a lot better.
Okay. Next question is MIDI 2.0 going to contain a predefined set of expression types?
That's going to be it's a separate thing. So as far as all the profiles and being able to do the node attribute data, that's something that there is going to be documented, a well-defined process for creating a profile that includes those kinds of things. And anybody will be able to do that. If a manufacturer wants to invent a profile for their own unique instrument, they can do that, publish the data, and other developers will be able to make use of it. If it's something broader than that, it makes sense to kind of bring that inside of the MMA, so a wider group of manufacturers can agree on how those things should work, so that people don't get left out.
Great. Another question is, so with MIDI 2.0, will it become possible for MIDI 2 instruments to represent whatever SFZ sound fonts have? Did the standardization group compare the features? For example, does it also have key switches?
Well, the thing is with node attributes, the idea is that you no longer need key switches. So then, the players that consume the SFZ data would just need to be able to translate between those existing key switch identifiers and using the node attributes. So I think they're kind of orthogonal.
Okay. And is there any information on what the support from different operating systems will be like for MIDI 2.0?
I wish we knew. I can't wait to find out. The people from Apple get very prickly if you start asking them questions. And I did speak with somebody from Microsoft who was much friendlier about that, but still not any more revealing what the plans are.
Okay. And will there be something like a standard MIDI file format for 2.0, or will it be the same?
Yeah, in fact, there's just a new working group that's in the process of forming to discuss that, which I'm joining, but has not yet met. So, but yes, there will be a standard MIDI file too.
Okay. And I'm not sure if I understand this question from Tom, but will there be a general MIDI 2.0?
That's going to be, again, with the profiles, that's probably going to be one of the profiles that comes out, is General MIDI 2.
Great. Okay. Well, that's all of our questions from the chat. Thanks once again, Brett, for joining us. Fantastic.
Eventually.
Yeah, and wow, and Bogdan had to unfortunately leave a little bit earlier, but thank you so much to Bogdan as well for joining us, and Christian, thanks for your presentation. I think this is such an amazing gathering, and I really think this is something really positive here that is happening, and it's something that we need to continue on. And that really brings me to just a reminder for people that are just joining, be sure to join us for the May virtual meetup that's going to be happening. It's actually Tuesday the 12th of May. I've actually put the flyer wrong. And we're going to have guest Stefano Zambone, who's the CTO at Elk, who's going to be speaking, and we will have more presenters. That will bring me to the other announcement, which is if you would like to submit a talk, we are welcoming submissions, demos, and presentations, and you don't have to be a 20-year veteran. If you're just getting your start in audio development and have something interesting you'd like to show us, please, we'd love to hear your ideas. You can submit a talk on the audioprogrammer.com/submit a talk. And I will say one more thing. For people that are looking to have more discussions just about audio programming in the community, you can join our Audio Programmer Discord group. You can join that at theaudioprogrammer.com/community. Join us there. So yeah, any thoughts, Timur? This has been a great meetup, hasn't it? Oh, you're muted. You gotta unmute.
Hang on, I was muted. Okay, sorry, I'm not used to this yet. I've learned so many things tonight about like mind-blowing tools and interesting effects and like MIDI and other things, and I'm just really happy that we could like sort out the tech to make this happen, and that so many people have tuned in. So thank you very much for joining us, and thank you to the speakers taking the time to record the talks and be live with the questions.
Yeah.
I would like to add that if you want to do a talk here, it doesn't have to be like one of those fleshed out like 30 or 40 or 50 minute things. It could be something shorter as well. Yeah. So I think the barrier to doing that is quite low. If you have anything that you're excited about, that you're kind of working on, or you want to share, maybe a new tool that you discovered, or a cool new programming language, or some audio technique, or like a cool effect, or whatever it is. If you think it's related to audio programming, give us write us a message on this URL that Josh just said, audioprogrammer.com. What is it? Submit
a talk. So the audioprogrammer.com/submit-a-talk. Yeah,
so please do that, and let's have these every month, and I'm really looking forward to how it's gonna be, how it's gonna develop, and looking forward for new amazing content next month.
Yeah, and another thing that I should mention as well is that I forgot what I was going to mention. Oh yeah, the talks from this evening are going to be uploaded separately. So any sort of hitches that we've had in this meetup will be you'll be able to watch it interruption free, and they will be the audio quality will be pristine. I promise, or your money back guaranteed. So yeah, we really appreciate you joining us, and this I think is so important for us to really gather as a community and continue to share and continue to push this forward. And that's all I've really got to say.
Yeah.
Anything to say, Christian or Brett?
Yeah, I mean, thanks for organizing this. I mean, this was a great opportunity to let me speak, and I hope to see this continue to grow and have more awesome talks.
Yeah, absolutely. Yeah. Well, thank you so much. And I guess this is the point where we sign off, and we will see you next month. Once again, don't be afraid to submit a talk. You can pre-record it if you wish, so you don't feel the pressure of having to perform live on the spot. And anything else, feel free to reach out to us, please. And I think that's it.
Yeah.
Yeah. Cool. Thanks.
Do you want to thank our sponsors?
Oh yes. Can't thank.
Yes.
We must thank our sponsors once again. Thank you to Focusrite and Sonox for their continued support and for sponsoring the meetup. If you're interested in supporting the meetup, please drop me a line or drop Timur a line, please. I'm pretty sure you know how to get a hold of us. And and once again, be sure to check out Juice, the announcement for Juice 6 as well on forum.juice.com. And we will see you next month.
All right. Thank you, and see you next month.
See you next month.
Right on.